Ted will be so lucky remains to be seen. Now, quick warning, I'm not expecting you to be able to read this next chart. It's just to show this is the sort of the outputs of the whole model, and puts together the low and high renewables scenarios with growth and reduction in demand, looks at capacity and at generation across all of the strands. This table, though, just for simplicity, excludes the electric vehicles and electric heating. So with this table you get to a total where in 2030 renewables are generating at our bottom line between 89 and 185% of Scottish gross consumption. And gross consumption includes the losses and the generator's own use. So if you're running a big power station, you actually use quite a lot of the power that it generates to, for instance, scrub the sulphur dioxide out of the flue gas. If you have a CCS, carbon capture and storage plant on it, you'll use even more of your own power to capture that carbon. So that's included in this label of gross consumption, rather than being what ends up in our houses and offices. Now, it would be, I'm afraid, too simplistic to say, well, if we've got 185% from renewables, can't we just close those remaining fossil fuel plants and job done, we're decarbonised? Well, that would be too simplistic. We need to ask whether we can do that without putting security of supply at risk. And that is probably this is where it gets complicated. I was thinking of trying to add it up as I went along on here, but I think it's going to be too complicated for me to do that. We'll maybe come back to that in questions. But the first thing to note is that things like wind and wave power, yeah, they are more variable, and in particular they are not what the industry would call dispatchable. So with a coal-fired power station or a gas-fired power station, it's the operator that turns the switch to decide when there's power coming out of it. That's dispatchable. With the wind, it's when the wind blows that decides whether there's power coming out of it. But there are sorts of renewables that are dispatchable. Reservoir hydro, for example. The water sits there. When we want power, we let some of it through the turbines. The biomass plants. Again, we'll talk about those in more depth later, but they are technically dispatchable. The economics don't quite add up for them to be properly dispatchable, but technically they are. But the less dispatchable plant in total you have in your mix, the larger the margin you need of capacity over your demand to allow for the fact that is more variable. But it's worth noting that in this model, then you've got a basis, and I'll explain this in a moment, a base of about 2 to 2.9 gigawatts. Now we're talking capacity here of dispatchable renewables by 2030. What I should have said is that the key test for security of supply is whether you can meet the peak demand in the system. The peak demand in the Scottish system comes on late winter afternoons and is around 6.1 gigawatts. So dispatchable renewables aren't even halfway there on their own. So I'm not claiming that they would do it on their own, but I'm going to try and do some of this adding up. So let's put that up here. So 2 to 2.9. I'll just call them DR for now. So this tries to put the two cases together. So you've got the low renewable scenario, the different components of it, and the high renewable scenario either side. The middle column shows the demand. And what we've done here is we've added in the heat and the transport electricity use. So again, it makes the same basic point. This top block is the remaining thermal power, the coal and gas. So it's much smaller in the higher renewables one. In this we actually asked them to model one that included a new power station. So we wanted to understand whether that was necessary and how it would work. So that has a new power station in it. As you can see, in the low renewables, the renewables are only just sort of getting there on the low demand level. Well, that's low demand plus heat and transport, and the yellow block on top is what the high demand would do to it. So the thing to take away from this graph, though, is that you get in the high renewables one over 150% of the likely demand from those high renewables across the average of the year. Now at the moment we get about 130% across the average of the year from all our generation. So we're pushing up that plant margin. Yeah, the surplus can be exported, as long as we can export it when it's there and surplus, which is the advantage of being connected into a wider grid. Now this is, I suspect I'll get some shaking heads on this one, so I know where I am. Our analysis then, or Garrad Hassan's analysis then goes on to be completely and utterly certain that it is technically possible. They're very clear that they don't want me to say, and that I shouldn't say, it is the optimum approach, but they say it is very definitely technically feasible to close down all conventional thermal power in Scotland without putting system security at risk. I've got a shaking head. I'm sure we'll have to pick it up in questions, but I'll try and take you through why Garrad Hassan believe that to be the case. And let's be very clear. They don't mean no new thermal capacity, they mean no conventional centralised thermal capacity. So it means closing Kirkensey, Huntston, Torness, and closing Longannet and Peterhead. Indeed, they think that it's quite possible that the operators of those plants might seek to close them because there's not enough demand for their services to keep them running as in the system, because there wouldn't be the capacity to transmit all of the power that they could generate. But let's not go to there for the moment. The point is, we could choose to retain some with carbon capture and storage, but the analysis says we don't need to. And what we do need is to ensure that we have the right infrastructure to manage that. And that is about storage of electricity, it's about deferrable demand, so that we can reduce that peak demand, and it's about interconnection of the system, so that when there is little or no non-dispatchable renewables, so no wind and no wave and no power available, we can import from elsewhere in the European grid. Those are the challenges, and we are, I'll again be honest, we're more optimistic here than the Scottish Government. The Scottish Government last week put out something where they said they thought that the system would need 2.5 gigawatts of thermal capacity to be secure. They didn't say how frequently that would operate, and I found it very interesting that 2.5 gigawatts on a pro rata basis is very similar to the figure that the European Climate Foundation identified as a proportion of capacity for the whole of Europe, and they said that would only need to operate for 8 or 10% of the time. So it'll be interesting to drill down into that Scottish Government research. So we've seen there's enough gross generation. The question is, can we get enough at the time we need it? Well, we've got this to start with, and our target is exceeding 6.1, so that's the peak demand. So the things I want to take you through, I'm trying to speed up because I think I'm going to run out of time very quickly. It's deferrable demand for a start. The idea of getting electric vehicles onto the system and electric heating does add to total demand, But the form of that demand is very different in that the electric vehicles